When analyzing a situation, system or an organization, it sometimes appears as if everything is connected. If one thing changes, another thing happens. This means that the elements have a certain relation to each other. These systems are called complex systems. Complex systems are dynamic because of their continuous ability to change, adapt, and reorganize in response to their environment. Imagine being a forester, and you need to know why the bird population in a forest is changing. At first, it seems simple. Birds are born and birds are dying. But when you look closer at the system, it turns out that the birds are also moving in between forests, and that this is due to a change of weather. But there is also a predator moving in because of the changing weather, which also affects the bird's population. All these causalities can get convoluted very quickly. To map out all relations, a causal loop diagram can be used. The function of a causal loop diagram is to map out the structure and the feedback loops of a system to understand its feedback mechanisms. A CLD is used to understand how behavior has been manifesting itself in a system so that strategies can be developed to work with or counteract the behavior. A CLD is also used to see how and to what extent the problem is connected with other systems. It is important that the CLD mimics the structure of a real system well enough that the models behave the same way as the real world would. So how does a causal loop diagram work? First, let's look at the simplified example of the bird population. A population is affected by birth and death, which means an increase and decrease of population. These elements are called variables or agents. The variables are connected with pointing arrows. The elements are of a certain size and the arrows show the direction of the relation and if the relation is positive or negative. A positive link means that if the cause increases, the effect increases and vice versa. In this example, an increase in birth leads to an increase in population. A negative link means that if the cause increases, the effect decreases and vice versa. In this example, an increase in death leads to a decrease in population. As you can see, loops are appearing. Feedback loops are the interconnections that illustrate self-organization in complex systems. The behavior of complex systems is in large part the accumulative effect of positive and negative feedback loops. For every feedback loop, a reference behavior pattern can be drawn to understand the behavior of the system. It is a conceptual graphical representation of the behavior over time of one or more variables. The loop that contains death is a balancing loop, meaning the graph levels out. The loop with birth is a reinforcing loop, meaning it will exponentially grow. The population is a self-regulating system. Self-regulation is a concept used to describe the adaptations of systems to their environment and how systems organize, change, or innovate. This example is of course an extremely simplified version of reality. In reality, there are a lot more factors and variables that affect the population. Now that we understand how causal loop diagrams work, let's take a look at an important and very actual complex problem. Climate change, the energy transition, and how this affects the Dutch electricity grid. Let's take a look at the first loop in the system of the energy transition, starting at the fossil energy use. Our energy nowadays mainly comes from fossil fuels. Unfortunately, the more we use, the more greenhouse gases we emit. This results in a higher rate of global warming, which leads to a higher urgency to transform the current way we use energy, thus increases the progress of the energy transition. In turn, this leads to more renewable energy sources like solar panels and wind turbines, and vice versa, the energy sources lead to an increase in the progress of the energy transition. Logically, the renewable energy sources lead to an increase in the use of green energy, resulting in a decrease of fossil energy use. Now that we have seen how climate change and the energy transition affect each other, we can find out how the energy transition affects the electricity grid. What is happening here? The variable renewable energy sources not only have a positive relation to the progress of the energy transition, but also lead to a surplus or shortage on the electricity grid. This is because renewable energy sources are weather dependent, meaning that there is only renewable energy sources available when the weather allows it. The surplus or shortage leads to an imbalance of the electricity grid. This is solved by curtailment of renewable energy sources meaning that the electricity is cut off. Although curtailment brings back balance on the electricity grid, it also leads to less use of green energy and thus slowing down the energy transition. This is where TROEF comes in. TROEF is an initiative with a mission to accelerate the energy transition by developing a new energy ecosystem while maintaining the status quo of the current energy system and making it more affordable for common households. An energy ecosystem is a system where communities in which both private and commercially connected participants can exchange locally generated renewable energy with other participants. Through market mechanisms, demand and supply will be balanced. Implementing this new energy ecosystem using smart tools and services can give people insights in how, when, and what type of energy they are using. This data is also comparable with their local energy community. Because the source of the energy can be traced, the decrease in carbon footprint can be substantiated. Let's go back to the CLD to see how TROEF influences the energy transition. The surplus and shortages on the electricity grid result in volatile energy prices. Consumers that make use of better selling and buying opportunities get a lower electricity bill. This attracts new TROEF participants. More TROEF participants means a bigger TROEF community. This also works the other way around. A bigger TROEF community means more participants. A bigger TROEF community also means more flexibility on the electricity grid. This will lead to less surplus and shortages on the electricity grid, thus enabling the acceleration of the energy transition. By looking at the reference behavior pattern of the energy transition, we can see that the energy transition is proceeding but is slowed down by the imbalance of the electricity grid. The reference behavior pattern of TROEF shows that the imbalance of the electricity grid decreases. By putting them together, we can show how energy transition is changed by TROEF. With this causal loop diagram, we can see where TROEF fits in the energy ecosystem and what agents have influence on the current energy transition. With this diagram, we can also see what elements influence each other and how this would influence the energy transition over time. However, the CLD is just a model, a simplification of the real world. Conclusively, let's look at the strengths and weaknesses of CLDs. Pros are the strategic overview it provides, and the model is easily explained. On the other hand, CLD has its limitations. A CLD could lead to incorrect inferences about the dynamics, which in turn lead to a faulty model. Secondly, there is no distinguishing between physical information and links. Lastly, there needs to be a clear agreement on the use of words and terms to prevent misunderstanding of the effects.